Hello, my name is Jan Brugard, CEO of Wolfram MathCore. Together with my colleague Patrik Ekenberg, I will be presenting how SystemModeler can be used in education. To give a short introduction of what we're going to talk about. So lately more and more universities and also high schools have been adding SystemModeler to the licensing. And the challenge is often that teachers don't know really how to use modeling and simulation in general. And so we started to meet one professor of another, and we started to talk to them and say, okay, what kind of challenges do you have with your course? And often say, okay, we are trying to teach complicated stuff, concepts, and we have to take shortcuts because we don't have enough time to actually demonstrate the students what we would like to demonstrate. We talked to the students, and they had a similar experience that sometimes they kind of were left with big holes in the actual pedagogical part of it because there wasn't enough time to do it. And we're thinking, in many cases, probably you can solve that by applying modeling and simulation. But the problem is that teachers are not really used to use modeling and simulation in many courses, and they don't have that much time to actually develop courseware, new courseware. And you don't have time to teach the students a new software at your course. A little bit like Paul Abbott was talking earlier today. So what's the solution to that? Well, our solution was, it seems to be a common problem. There should be a common recipe. We should be able to supply like a starting point for teachers so they can use modeling and simulation in their courses. So what we did, two of the students we were talking with, Emil and Alexander at Linköping University, were students has two different Master of Science programs at Linköping University. And they were having these problems. They were going a couple of courses where it showed, okay, we're not doing exactly what we should do to really learn the course. So say, okay, if you come to us during summer as interns, and we work together with the professors, can we try to find ways to illustrate the things you have problems with in your course in order to take you to another level? And that is basically what we're going to try to present here. The two things that I have worked on, and then a third course that we have kind of worked internally with without any contact with any of the students or professors, just to kind of see if the recipe works on courses where we don't have contact with others. And with that, I kind of leave this for Patrik, who will present a biochemical engineering course. Let's do.
Yeah, that could have been more agile, but here we go. So one of the professors that we talked with he was teaching this fourth year bioengineering courses. And it's really amazing though, because when the students, they get there and it's a project course and they get to do all this kind of cutting edge research, and they work together with researchers out there who are doing actual stuff, and they get to apply the knowledge and the stuff that they are working on. It's really something that when they get out of university, many go on to work on this. So what they were doing was they were recreating, reconstructing biological and biochemical networks. So you had like different processes, some different processes in the human body, or some different processes maybe in bacteria or other organisms. And they tried to figure out what was going on there. But one of the problems the professor, he mentioned to us that when they got to this really applied, this project course, they were expected to know very much, they were expected to know these theoretical concepts about biological networks. But the students simply, they hadn't acquired that knowledge yet. And to formalize, some of the problems he mentioned for us was simply that the complexity, they studied some simple biological networks, but the complexity of it was not sufficient for the courses down the line. And it simply wasn't applicable at the master's level. And since there were many students, many students said that this is the course that when they go out and work, this is the course they have learned the most from. These kinds of concepts would need to be applicable in a work environment also. So let's see, I need to evaluate it, sorry. Right. So we took a look at how the courses kind of looked today. And for this, we will use a running example, and the example we will use is enzyme catalysis, enzyme kinetics. And just to give you an idea for you, I realize many of you here aren't from a biochemical background, so just to give you an idea why this is important, enzymes in your body facilitate almost all reactions, I believe. And without them, these kinds of reactions would be possible, but would take a very long time. I believe I read somewhere that one of the key ingredients of the synthesis of hemoglobin, the stuff that binds oxygen when you breathe, that binds oxygen to your blood, the synthesis of hemoglobin would take about 2.3 million years if you didn't have any enzymes in your body. So imagine going out giving blood and then you have to wait 2.3 million years before you get any more blood. That would be quite horrible. So we could look at a schematic of how these enzyme catalysis, is that right? Oh, well, how this works. So in the simplest scenario, you have an enzyme, which is a protein in your body, which binds to a substrate. So for example, you had lunch recently. One of the proteins, one of the enzymes in your body, binds to the proteins in your lunch and breaks it down into smaller, more manageable components. So this is what happens here. The enzyme binds with your food. It forms a sort of substrate enzyme complex, and then at the end releases it. And this curve here is the energy expenditure. And now the food could break down on its own depending on the environment, but it would take a very long time. And we can visualize this this is a SystemModeler model built using the biochem library, and this shows exactly the same thing as the schematic over here. You have the substrate. It goes on together with the enzymes and forms a complex, and then at the end releases the enzyme back and forms a product. And also you have a pathway here in which it just breaks down on its own. And so you might realize that how fast things like this are happening is a very important subject. Even though your body strives for homeostasis, it wants to remain constant. You don't remain constant during the day. You eat stuff, you exercise. So all of these processes happen, and they take some time, and the dynamics of those processes are really important. And that is what you can use systems models to understand. And you could also do like traditional learning. And how could you study this traditionally in, for example, a biochemistry book? Well, you could, for example, look at all these four substrate here, all components here, and then do a plot over time. So you can see how things changes over time. Well, we start with an initial amount of substrate. It goes down. First it binds with an enzyme forming a complex, and the product goes up. But this is just one slice of reality. In actuality, all these different pathways, all these different substrates, initial concentration varies, the catalytic activity of the enzymes varies, and this is very important for the body's ability to regulate how much sugar is in your blood, to regulate the enzyme activity. So these are all different parameters, and what I just showed you now was one set of parameters, and doesn't at all paint the whole picture. So how could you study that? Well, traditionally, you could do a plot. You look at, for example, the amount of free enzyme, which is the one here, but how it would look if the parameters were at different values. The parameter kcat is the reaction rate happening.
Just to break in quickly, when he says traditionally, this is the way it's taught right now at the
right.
course, like before they apply to SystemAller.
Yeah, but what is lacking from this, this learning that they are having today is, well, the professor felt like, they aren't quite getting the intuition from these kinds of graphs here. They aren't quite getting the intuition that they need to understand the dynamics. And, this example here is just one very simple example. So it was just 4 substrate. That is not how it looks in your body. And these are the kinds of things we are teaching to our students traditionally, but and they are expected to infer kind of a network behavior just from those simple components. And that is not at all how it works when you connect it all together. So how did we want to tackle this problem? Because we had really good contact with this professor, so we sat down and thought, okay, how are we gonna, what can we do about this? So we had one summer intern here, Emil Arkstål, during the summer, and we gave him a 2-day SystemAller and Mathematica crash course, and asked him to, with this traditional learning, narrow down what is it that is missing. So he was thinking about, okay, so and he has taken these courses, so he was thinking about, all right, how would I have liked to learn these concepts? And he came up with an implementation that where he created student assignments that they were allowed to, they got a problem and they were supposed to solve it using Mathematica and SystemModeler, and also implemented demonstration for how this could be applied in a biochemical network, in larger biochemical pathways. So let's look at one of these. And in fact, the running example I've used is from one of his assignments, which deals with enzyme reactions. And this was one of the ones I actually almost took credit for. This is one of the models he built, where we study the reaction rate of an enzyme. And having this model, it allowed the student to look at different parts of the process and for themselves set different values to these parameters. So I could, for example, look at, all right, what happens if I change the kcat parameter to 1 or to 2 and to 3 or 4. And right now we were looking at the free enzyme. We could also look at the product formation. So the students can use this and try for themselves to see how the system responds to their inputs. It's not just a static image in a textbook anymore. It's something that they can interact with. And in fact, when we're talking about interaction, he went and took this one step further, where he implemented interactive manipulates, where you could drag in different sliders like this. So here we have 4 different parameters affecting this simple system. We have the binding rate between the substrate and the enzyme. We have the reverse. Sometimes the complex just lets loose without it going further and forming a product. And the kcat and the other one down here. So they could manipulate these for themselves and directly see how these parameter values affect this model that I've just shown. And we believe this is something that will give kind of the intuition to the students to how these systems work. And these are just some of the parameters we could include. For example, the starting value of the enzyme, the starting value of the substrate, and this is then used to, answer specific questions about the system. So if you have, you have 0 binding rate, the enzyme and this reaction here, it doesn't happen. Then you'll see that that is one of the questions, and then you see that, oh, well, these parameters, they don't affect the system in any way. But this one, the non-catalytic reaction, the one there which just breaks down spontaneously, that affects the system. So this is kind of the intuition you can get from this. And so this was dealing with kind of the knowledge of the system dynamics. Now, we still haven't talked about larger networks, but the nice thing here is that while we've been doing this, and this is a model here that you might, a professor might give this to a student that it's pre-built. The students don't have to do anything. They could just play around with it. But now they have this model. They've familiarized themselves with this model. And then they can do all these nice things. So instead of, building this from scratch and seeing how everything works, they can take this and do slight, let's see here. This is SystemModeler, by the way. I don't think we've shown this yet. Right, for you who aren't familiar, this is SystemAller. So this is where the model was created. So they can do all these modifications and get a better understanding. So if I change this to an ambient substance here, what happens now is that after the enzyme has reacted, it goes away. It doesn't exist anymore. This could, for example, signify that the enzyme would break down after the reaction. Sounds very bad, so hopefully it doesn't do that. But they can do this. They familiarize themselves with the model, and they can do this, these kind of modifications for themselves and see how it affects the system. So now the substrate and the enzyme actually has the same concentration because they start the same, and when the substrate depletes, so does the enzymes. And what is nice is you can go back to the manipulate we had here and reevaluate. So you can still use these kind of pre-built control object, and suddenly we're no longer looking at the professor's model. We're looking at, I think that I might have used the wrong one. Okay, but instead we're no longer looking at the professor's model. We're looking at the students. They modify these themselves. They are the authors of the model. And in fact, this can get one of the courseware that Emil developed was something where, this is in principle the same as the enzyme model that we've looked at previously. We have the complex here in the middle, but instead we have 2 substrates. We have one enzyme that can go to different conformations, and we have 2 products and stuff like that. And it's just a bigger modification of the model. And instead of just having the small components and inferred network structure, they can actually start and build up that network structure from the small components. And the verdict here was that they were very, very impressed and want to implement this in the biochemistry course that's due this spring, I think. And also, in fact, the larger model that I showed here, they want to use that in a higher education biochemistry course where they do more kind of applied research and of course, a very important part also is the thing that these interns we had here, that they learned. They felt that they got a lot from modifying these, and they learned things about the subject. They were third year students maybe, and had gone through these courses, but they learned so much more by being able to manipulate and build these structures for themselves. And now,
I'm
John,
switching in. If you have any questions for Patrik here, well, I'll switch in quickly.
let's see if you're more nimble than I am. How do you plug this in?
Do you have HDMI input?
Yes.
Here's the adapter.
That was.
HDMI. Do you need network?
Nope. Oh, that was the wrong adapter. I have an adapter.
Oh, there we go.
Oh, you had it. Okay, so this should come up soon, I hope.
It's not plugged in all the way.
It is. Let's try my adapter. No, that's the only one.
Okay. Yeah.
that I have. Let's try this. Yep. Okay. So that was a biochemistry course. Then we looked at something that should be kind of completely different. And what we chose was a CDIO project course where the students were supposed to develop a sunlight simulator. So that course was also from Linköping University. We're based in Linköping, so it's just next door to us, so it's kind of easy for us to interact with them. And the goal from this course was to develop this sunlight simulator for the students in a way so the researchers later on could use that in their research with small modifications. So it's a pretty high level of goal here. The students were second grade, so they didn't have that much theoretical concepts in their bag, so to speak, when they came to the course. The setup of the course is that they have these LED matrices, 8x8 LED matrices, that they will try to control in order to simulate the sunlight. Then they have DAQ cars, LabVIEW, measurement equipment, and so on. And the setup is something like this with, well, you will actually understand some of the Swedish words, like positive lens. You can understand that, right? But basically, this is the setup they are trying to construct. And in order to do that, what they do is basically they first start by designing the different parts. So for instance, designing the electrical circuit. And we'll look at that part. How did they do to design the amplifier system for each channel of the LED matrix? Well, the students started by drawing their analog circuit, and it looked something like this. Then they went to the professor or the assistant, showed it to the assistant, said, okay, does this look good? And the assistant said, great, perfect. You've done exactly what you should. However, he says, and it's perhaps a little bit small, let's see. However, he says, the world is not ideal. And you have worked with ideal components. So he takes their suggested circuit and says, you should add a capacitor here, another capacitor here, and that capacitor should have this value, and that one should have this value. Now, start implementing. And then, okay, they did that. But of course, they were left a little bit cumbersome. The problem was the students didn't really understand that there was something with non-ideal world that they had to take some kind of account for. But there was the assistant doing that for them. And this was a frustration for the assistant, and it was a frustration for the students. Well, why are you doing it this way? Well, because the tools he has, we're using SPICE, are too advanced in order to show the non-ideal effects. It costs too much. There's no time to do that. So he said, OK, I don't see any solution to that problem. So they were basically left without really feeling that they understood this step, which was very important. So even if they succeeded with the project later on, they did that with a minimal feeling that we cheated. We didn't get it entirely. So one of the students, Alexander Nass, just as with Emil, we gave him a 2-day SystemAller Mathematica crash course, had never used any of the softwares before. And then we started to discuss a little bit of how non-ideal effects could be illustrated with him and with the professors for a couple of days. And then it was up to him to see if he could resolve the problem. So what he did was a few demonstrations or manipulates that he basically to teach himself, but that then can be applied for students. So let's look at those for one of the things he did. So he has this. This is basically a very small version of what they were supposed to do. So this is how the student solution looked like. Because now we have ideal components here. Everything is working perfectly fine, as it should. And his first assignment to the students is this, and I should have kind of shut that down. This small manipulate, where you can see that how does this kind of OP amplifier work? Doesn't matter at all if we here understand an OP amplifier or not. But basically, an ideal OP amplifier will take, if you have the right-hand resistor that with 100K ohms, divide that with the left hand, 10, then you have the magnification. But this is also inverting, so it will be negative 10. So they did, he basically made an application, a small manipulate where they can change the resistance and see how it changes. Kind of boring. But this was basically the level of understanding they had in the course when they designed their analog circuit. So next thing he did is, so let's switch this to a non-ideal OP amplifier instead. So the circuit basically looks the same. The OP amplifier has a little bit more details inside it. And then let's look at how that would kind of behave. So suddenly, here we see there's some kind of overshoot. It's the very same circuit, but there's overshoot. And now if they start changing here, we'll see, OK, that changes there, increase this, I'll have that effect, and so on. So suddenly here you see, OK, the world, if you made the same here, in their ideal world, it would look perfectly. I can go back instead of like 55 and 35. Can go up here, choose something similar. 55, 35, doesn't matter if it's exactly the same. This is how they believed it worked previously. But by sitting here with this small circuit, and they can play around and say, OK, this is the type of effects I actually get from my circuit. Suddenly they get an understanding or why they need these capacitors. So next step he does with this one is that he adds corrective filters. And the difference here is he has added this capacitor here and this one here. Otherwise, it's the very same circuit as the previous one. And now with those corrective, and this was what they got from their assistants before. That was the capacitors basically got on the slightly larger circuit, but they got those. And then this is the kind of response you get then with the amplifier. So we don't have the overshoot. It looks nicer. And we can start to kind of play around with these guys here and see how it works. So we see that these capacitors actually have an interesting effect. So what's the next step? Well, the assistant, of course, he gave him the values of the capacitors also. So why not allow them to actually manipulate the capacitance of each capacitor, like increase this one, decrease that one, and see how these actual values affect the circuit. Some with these small apps that the professor, or in this case, one of his students has developed, he can supply that to the other students of the course in the future, and they will be able to play around and actually realize why are these capacitors needed, and even by themselves choose the right capacitors rather than having the assistant giving it to them. So that's pretty nice. So with that said, and then I will go quickly, afterwards he started to do, oh, this is fun, so can we do a little bit more? So he started to do other, like longer assignments with introduction, some questions, a little bit more in programming and so on. And we believe this is kind of what will happen once you start to actually see the fun of it. A few students will want to do this extra, and the professor will say, "Oh, then I want to teach. I want to teach this and teach that also." So also adding those to other courses. So basically, yet again, the professor, the assistant, and the students were very happy with what they got from an intern project. So then, okay, if from two courses where we worked together with students and professors, it turns out that it was pretty easy for the students to actually reach another level for the course. Now, the professors are not stupid. They're good professors. But still, a student could, with some assistance and some discussions with us and the professor, add value to the course in such a short time. That's pretty nice. So suppose that we would try to do that on a course that we're not involved in. So we looked at the MIT OpenCourseware, selected the Mechanical Engineering Dynamics course, and took a look at that. And now internet is probably not working, so I'll go this. So this is basically how MIT open source courseware looks like. They have tons of courses. They will have some description of the course and a bunch of different material like quizzes and so on. They will also have, so in this particular case, the course is taught for undergraduate level in mechanical engineering, and they have the goals of learning a few different concepts, okay? So let's take a look at that. So how do they do that? Well, what they do is they get textbook. For some reason, that opens up a little bit down here. They basically get this PDF with, doesn't want to zoom for some reason. Can I zoom here instead? Okay, but there you go. Okay, so basically it's a bunch of text, some figures showing different mechanical. Here's a beam with a spring and position somewhere. And then equations, more text, more equations. So this is basically what they're learning, which is, of course, that's what they're supposed to learn. But note, there's not one single illustration of what's actually going on. If we look at one of those exercises get is within Lagrange equations. So basically, mechanics are taught. You can either teach through classical mechanics, which in Sweden we almost only teach classical mechanics, or you can use Lagrange equations. In France, they almost only use Lagrange equations. And then in some countries, like in the US, you use both, depending on professor and so on. But anyway, so in this course, they're using Lagrange equations. And they get different problems like this to resolve. Oh, there, should have seen that before. And they're basically supposed to solve these equations and set up the system of equations for solving Lagrange equations. Their solutions will look, we'll skip that. Their solutions will look something like this. We're looking at a spring, for instance. Will be similar. This is from the book. It will be these equations. In our perspective, we work with equations all day. This is fine. This is great. This is, of course, what describes the problem. But how many here actually could tell me how this system behaves from those equations directly? It's a very simple system, spring, mass. How does it behave? Do we think that the students will understand this? Most of them will not, I'm pretty sure. You could use Mathematica, of course, to solve Lagrange equations, these equations, and get some plots and so on. I will not be doing this here for the sake of time, but you can also model the thing in SystemModeler. So if let me just close this so we see them together. If we see this, we have the spring and the mass, and this is basically the same that we have modeled in SystemModeler. So if I take this model now, and let's open it in Simulation Center. So now we will simulate this in Simulation Center, and it will give us an automatic plot of the position of the pendulum. How many saw that from the equations? Hand up. Probably none. It's kind of difficult to understand, right? But now you can get this, and why does it look like this? Well, we can, in this case, this is the system with a spring. We have a very weak spring. And of course, depending on the frequency here and the spring constant, now this spring has actually, there's a spring in both x and y direction, so it can twist in both. And depending on what you set values here, you will get different behaviors. So now you can test your equations and see what will happen. And we think this, like just giving this model so they can relate the equations to some reality will help them quite a lot. Okay, so in the same way there, we think that once they have actually been able to solve something like this, and he did, and we did several different similar material for them, perhaps they would like to do more advanced stuff. Perhaps a few of them would say, oh, okay, this was fun. Let me do more stuff. So we created some more advanced assignments. And for instance here, we will have an assignment with a double pendulum instead. There's no springs involved in this case. And we'll give the students questions of different types, like the same type of questions that you actually get in the current course. We also have the solutions here. So they're actually supposed to solve these equations, just as they're doing today. But we're also supplying them with the models so they can try out this and experiment with it. And then we gave, okay, once you can, if you want now's when you understood this model, if you want to do something more advanced, because when you're doing more advanced, you will not be able to do that by hand any longer. Now, let's start doing a little bit of fun stuff here. Let's do life a little bit more complicated. Get this one. Try to see how that works. Perhaps develop a swing carousel. So let's look at how that looks like when we simulate. The model of this one is, let's see here if I can find it, pendulum with swing. Oh, this rotating swing, sorry. Okay, so basically this, all the things you see on the right-hand side there is different, each separate swing. And each of those separate swings is very much the same kind of pendulum model that they have already modeled. So just using again and again and putting it on a plate. And you can either, of course, supply this to the students so they get the whole solution and just can experiment just to see, give it some more like flesh and blood. They can probably remember when they were playing in the swing. I prepare this beforehand because it kind of takes I think 1.5 minutes or something like that to simulate. So, and even if we actually have some extra time, it will be quite boring 2 minutes to wait. So I prepare that. So let's look at it. Here it is. So here is what the model shows. And it will start rotating after a while, pretty slow. We are kind to our users in the beginning. After a while, probably, if you're on it and And you will kind of feel some, a little bit of trickle in your stomach or something like that. Because after a while, this will kind of have a spin and you can look at it. And then, of course, you can give them plots and show different forces. And suddenly, this Lagrange equation that I have has come alive with some small steps. And they really, for a professor to develop this material that we develop, for most professors won't have that time. So, of course, but if they had this material or had something to start with, they could do quite amazing stuff. So that comes to the, oh, this was the wrong notebook. Let's switch this one. Oh, sorry. Someday I will learn how to use Mac. So what we did is we started with these and a couple of other courses. Our idea is to start to actually make a bunch of different materials that we will provide over the web. And where do we think that this will be able to apply? Well, in a bunch of courses. Any course where you can use SystemModeler, of course, you could do this. It could be social science, or it could be chemistry or aerospace. It's not limited to biochemical engineering, mechanical engineering, electrical engineering. Those three are pretty far away from each other. Still, we could do pretty nice stuff that we think adds a lot of value to the students. So anyone that has an idea for a course that you would like us to help with, we are happy to talk to you. What we'll do then is kind of do similar things to here and make it available online in order to, I thought I had a slide about that, make it available online so other professors can download it, get inspiration, and use that in their courses. So with that, I'll thanks and questions.